Had from Friday into z-scores. Hopefully, you guys remember that the z-score formula was the value minus the mean over standard deviation. So we got to learn a couple things about this. Didn't you actually go figure out what the mean of this data was? It's around 33.3. And what was the standard deviation? Yeah, 36.4 something. Huge standard deviation. That should not surprise you. Remember, the mean and standard deviation go crazy when you have an outlier. Okay, so that large standard deviation makes sense. Okay, that outlier made it go crazy. All right, so how do we go about finding the typical standard deviation from the mean? Okay, you can do it all at once on your calculator. Okay, so here I've got my data in the first two lists. And I want to create the standardized scores. The measure of relative standing. These are all different ways of saying how many standard deviations you are from the mean. To do that, highlight the top. I hope you remember your parenthesis around the top, because if you don't, your calculator will mess that up. I want the actual scores, which are in L1, minus, and then we can actually go calculate the mean. I wouldn't want to put in 33.3 because that's an approximation. It's actually 33.33333, so I want the calculator to keep all of that. To find that, it's in second stat, which is the list. Go over to math, put mean. I want the mean of what? I want the mean of all the things in L1, two parentheses, divided by what the standard deviation of the L1s are. So once again, go back to list. 7 is standard deviation of the L1s, and there are the standardized scores. That makes sense. The mean was about 33, 45. That's above the mean. How far above the mean? Only about 1/3 of a standard deviation above the mean. And there's the big dog. Okay, that turns out it's over 2.5 standard deviations from the mean. Think about your tables and how far 2.5 standard deviation was on that high side. Same thing now with the response variable. This would be parentheses, don't forget. L2 minus, once again, the mean of the L2. Close off the parentheses, divided by the standard deviation of the L2s. And there are our standardized scores, the measure of relative standing. 76 is almost one whole standard deviation above the mean. So a score of 76 on the test, you beat the mean, beat the average by almost one full standard deviation. Now what I asked you to do was graph these. So let's remember what the original graph looked like. So if I go into my scatter plot and I graph the original data, and remember zoom stat's a nice feature when you're just trying to look for generalities. Go ahead and let the calculator figure out the window. Here were these test scores. Okay, there's that 126-minute studied score over there. So kind of get a picture of that. And now let's graph the z-scores. Go back in, change them to the z-scores. Once again, zoom stat. There's my picture. All right, Madison, talk to me. What do you like, different? What do you see here?
Are you comparing them or just?
Yeah, comparing those two graphs, the first one and this one.
The first one is mainly in the
That's the 25th percentile. I think you mean the first, start with the Q. Quadrant. Yeah, wasn't the first graph all in the first quadrant? Aren't all of these numbers positive? Now notice this graph, we find them in 3 of the quadrants. Why? Because when we changed them to z-scores, didn't we have positive and negative values here? If you have a score lower than the mean, your z-score is going to be negative. If you have a minute studied lower than 33.3, you're going to get a negative value. So absolutely right. I've got positive and negative values. It's going to be very important what I'm going to talk to you about in a second. How about the shape of the points, though?
It's the same.
It's exactly the same. Okay, so the points are going to be exactly the same shape. It's amazing, but they're exactly the same shape. Okay, but we obviously changed the actual values, and now we have positive and negative values for your z-score. Okay. All right, here's our goal today. On Friday, I just said, hey, what's that thing look like? Does it kind of look like a line or kind of look like a circle? What do the points come up with? Well, today we're going to focus on a straight line. How well do the points on your graph match up with a straight line? And it's called correlation. Okay, so for example, if I got a graph that looks like this, I want this correlation to say, hey, you got a straight line. In fact, you got a straight line with a positive association. I would like this thing to tell us that. Or, if it's like this, I would like us to tell, hey, you got a perfect straight line. Okay, but it's got a negative association. I'd like this correlation to tell me this. Or if I get a graph like this, that's a horrible straight line. That's the worst straight line you can get. But it does have a relationship, but it's just a horrible line. That's what correlation is going to tell us. It's going to tell us two things. Does it have a positive association or a negative association? And how well does it fit a straight line? Okay. Fancy formula. Go find it. It's on page 3 of your formula sheets. This isn't one you have to memorize. In fact, other than tonight's homework assignment, it's probably one you're never going to have to use again, but it is on your formula sheet, so I guess they could ask you if they wanted to. Alright, it's a little embarrassing, but I taught this class for about 6 years before I realized what this formula really was. I mean, I saw the formula and we did stuff, but I never quite understood what it was. Alright, a lot of fancy stuff going on in here, but what is this? What is this right here, this piece of the formula? It's a z-score. It's what you just did in L3. I never knew that. It's like, wow, that's a crazy formula. It's just the z-scores. It's what you have in L3 right now. And what's this guy? It's the z-scores of the response variable. It's what you have in L4. Now, how do you read this formula? And I put this in here just to make sure you know. Anytime you got 2 parentheses next to it, it means you multiply. So what this formula says is, okay, we're going to multiply the 2 z-scores together. Then after we've multiplied all the z-scores together, we're going to add them up. Then we're going to divide by how many points there were minus 1. So in this particular problem, there were 10 points, so we'd be dividing by 9. Now, like I said, somebody a lot smarter than me came up with this formula. But you're guaranteed, after you do this formula for any set of points, that your answer is going to be somewhere either -1 to +1. It's guaranteed. Can't be more than that. Yes?
Yeah, could you please explain the degrees of freedom concept?
It's not in this one. So you mean about using sample standard deviation?
The 1 over n minus 1, isn't that the degrees of freedom?
No, it's not. It's actually, this is how many, well, it might have something to do with that, but somehow it makes the formula work so your answers come in between +1 and -1. So I don't know if exactly it's degrees of freedom, but for this formula, it makes sure your answers are somewhere between -1 and +1. But we're going to talk a lot more about degrees of freedom later. It has to do with taking a sample versus the population. Okay, so here's what it is. If you get an answer after doing this crazy formula and it comes out to -1, you've got a perfect straight line going in a negative direction. If you get an answer that says +1, you've got a perfect straight line in the positive direction. And if you get an answer that's 0, it means it's the worst line possible. It's like a circle. Now, how in the heck does this formula do this? Well, here's how. It's genius. Okay, so let's say you've got a bunch of points, perfect straight line. What that formula does is it changes it to the z-scores, which we've just done, so it keeps the same shape, right? But it's going to create these axes. All right, now, talk to me. This particular point, the z-scores for both of them are positive, right? When I multiply those 2 z-scores together, I'm going to get a positive number. Positive times a positive, it's going to be a positive number. Positive times a positive number. Now what happens when I multiply these two z-scores together? It's going to be positive again, right? Negative times a negative. So for a perfect straight line, I just keep adding positive number, and positive number. Okay? But what about if it's a perfect straight line in the negative direction? So I got this. Pretend that's a perfect straight line. Okay. I'm going to change them to z-scores. So when I multiply these two z-scores, I'm going to get a negative number. Negative number, negative number, negative number, and negative number. So that when I add them all up, I get a big giant negative number. Then when I divide them by how many points I have minus 1, it's going to be negative 1. But let's say I don't have such a perfect straight line. Let's take a look at our line, for example. Now we already know that our line wasn't a perfect straight line. But it is going in a positive direction, isn't it? So let's take a look. When I multiply these two z-scores, I'm going to get a positive, a positive, a positive, a positive, 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 positive. It's going to add up a whole bunch of positive numbers. But aren't I going to be subtracting? Isn't it going to be coming down a little bit too? Okay, so that's why it's not going to end up at the perfect positive negative 1. Now let's take this situation. Let's say we got the worst line possible. Perfect circle. When I change these to z-scores, it's going to be adding up positive, 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 negative, 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 positive, and it's going to take me right back to 0. So like I said, I have no idea. It's brilliant. I don't know how it ends up at 1 and negative 1 perfectly. Okay? But that's kind of the concept of how it can get to a positive 1 and negative 1 when you're multiplying the z-scores together and then adding them up. In fact, now you don't have to guess anymore. I found this scale in another book. I think it's pretty good. So tonight you're going to be asked to go find the correlation value, the R value, and then evaluate it. I only want 4 words. Finally, you get to write a sentence that's really short. Okay? If you get an R value that's somewhere between 0.8 and positive 1, you're going to say you have a strong positive linear relationship. Remember, this is about a straight line. If you get something in like 0.5 to 0.8, that means you had, some negatives you were adding up to, a lot of positive, but you had some negatives. You'd say you'd have a moderate positive linear relationship. Okay, anywhere in here, it's a weak positive linear relationship. Hey, it might have a relationship, it might be like a circle, but it's not a straight line. Okay, same thing on the other side. When you get negative R values, it means the points were in general going in the negative direction. Yeah.
So if we ever get 0, we say there's no?
There is no relationship. No linear relationship, right? There could be a relationship. That's a circle. That's definitely a relationship. I can make a graph out of it, but I can't. There is no linear relationship at all. Yeah.
Would 1 be strong positive, or would that?
1's a perfect straight line in the positive direction. Perfect straight line. Okay. All right. So on your first homework problem tonight, you've got to go through this formula. So let's do that. Let's go find the R value for the problem that we just did. So we've already done most of it. We found all the standardized scores. So our formula says now we have to multiply them together. So let's go into your calculator. We'll put those in L5. Now tonight, you'll do these 5 columns. You'll put them on your paper. You'll show me how you got the R value. All right, so the formula says I have to multiply. These numbers are in our L3, right? These are the z-scores for these, and the z-scores for them in L4. So in L5, we'll multiply the two of them together. We're going to multiply those two numbers together. So L3 times L4. Make sure you're on top so it does it all at the same time. And this is the product of the two z-scores. And notice here, I've got the negative and positive. So that was that point over there in the second quadrant that gave you a negative product. So now we've multiplied the z-scores together. The next thing that we have to do on this formula is add them all up. That symbol means add them up. So we can do that with a 1-bar stat. Stat, calculate, and do L5. Calculate on L5. And there it is, add them all up. So adding them all up, we get 6.505. And what's the last thing on our formula asks us to do? We have to divide them by how many points I have, minus 1. So divided by 10 minus 1, and that comes out to about, what, 0.7227? So if you were asked to evaluate the linear relationship of this minute study to test results, you'd say you'd have a moderate or moderate to strong positive linear relationship. Okay? Alright, so this is number 24 tonight. You're going to show me all 5 columns, show me the math, and answer whatever questions it has about it. Alright, after number 24 tonight, anytime they ask you to go find the correlation or go find the correlation coefficient, I got a cool way to do it on your calculator nice and quick. Alright, so here's how you do it. The first thing you all need to do is something called turn diagnostics on. Otherwise, it's not going to show you the correlation. So to do that, go into your catalog, which is second 0. Now, if you guys go replace your batteries, or you go get a different calculator, you got to do this. So to remember this part of it, this is something you've got to be able to do to turn the R value back on again. Go to diagnostics on. Some of you calculator freaks know how to just get there real quick. I got to do this. Diagnostics on, and then hit enter. So that's just a little step that you got to do in order for our calculator to show us this R value. Okay? Alright, let's go find that 0.7227. How do I do that? You go to Stat, over to Calculate, and then down to number 8, Lin Reg A B. We'll find out what all that stuff means later. Hit enter. Alright, now if your data is in L1 and L2, which ours are, you're good. Just hit enter again, you're done. However, let's say your data is in L3 and L4. You would put L3, comma, L4. So, but right now our data is in L1, L2, so we're good. Hit enter. And there's our R. If we didn't do diagnostics on, it wouldn't show these last 2 rows. I don't know why. Okay? So after number 24 tonight, when it says, you know, there's your data, go find correlation, throw them in your calculator, go get the R, but then give me the 4 fancy words. Strong, positive, linear, or moderate, positive, linear association. Okay, yeah?
So then in tonight's homework we have to show,
On number 24 only.
like, basically what's in our calculator a little bit.
Yes, you'll write them on your paper. There's only like 5 or 6 points. It's not as long as even that one goes. Okay, so having been able to find R and give me the 4 fancy words are important, but this is the stuff that you got to know about R. These are multiple choice questions just waiting to happen. So if you've been losing a lot of points on multiple choice because they get a little tricky and they ask you tricky questions, these are the guys. So pay attention to this. You're going to answer a bunch of questions on this tonight. First things first. R, correlation, could care less which one you set up as your explanatory and which one you set up as your response. For example, we could have done give me your test score. I'll try to predict how many minutes you studied. I could switch these explanatory and response. We'd get exactly the same R value. We'd get a little bit different graph. You get the inverse, but you would get the same R value. Now, here's why. Let's go take a look at this formula again. Isn't this just the z-scores that are in one of the columns and the z-scores that are in the other column? What happens if I switch them? Isn't 2 times 3 the same thing as 3 times 2? Doesn't care. R doesn't care which order you put them in. So correlation's not going to change if you switch these 2 around. Number 2, they love this as a multiple choice question. You can only use quantitative data. These have to be actual numbers. If this was like football position compared to your test score, it ain't gonna work, right? I can't put QB into my calculator, right? These have to be numbers. You're laughing. There's a multiple choice coming to your Western way pretty soon. You're gonna Now be careful, you're going to miss that. Okay, so they have to be quantitative. All right, this is a biggie. R does not change if you change the units of measurement. Let me give you an example. Let's say instead of the raw score, I would have put the percentages. So this would have been 76 out of 80, so this would have been 95. And this would have been whatever that is, 97.5. And I would change these to the percentages. R would be exactly the same. Why? Well, what are these z-scores? It's the measure of relative standing. Wouldn't they relatively be the same place they were before if I changed them to percent? Another thing, let's say this was in feet and I wanted to change them to inches. I could multiply every single one of these numbers by 12. But their relative standing would be exactly the same. So changing the units of measurement is not going to affect the R value. You get the same exact thing because we just changed them to z-scores. Positive R value means those points were going up this way, right? In our z-score graph, we got more points in L1 and L3 that we were adding positives rather than the negatives. If the R value comes out negative, it means the points were going this way in general. Okay? So you can tell direction just from R. And sometimes you look at graphs and you're like, is that going up or down? R will tell you. R is always going to be a number between -1, could be exactly -1, or +1. One of the multiple choices, like R is 1.08. That's the one that's wrong. Okay, it cannot be outside that range. Don't forget now, R is only talking about how well a straight line fits those points. You could have a great relationship, a circle, or a perfect exponential graph. But that's not a straight line. R is going to say no good. But there still might be a relationship. Okay, so that's why it's one of our big 4 words, strong, positive, linear relationship. And then finally, just like other things we've studied, R goes crazy with outliers. Let me give you an example. So let's say I got this graph. I don't know, I got these points here, nice little circle. R is going to be 0. Put one guy out there, R just falls in love with that guy. Wow, I know where I'm going. I'm a straight line going that way. R goes to like 0.998. R can do this too. Say I got 2 points there. What's the R value going to be of this? -1. Oh. R goes to like +98. So R is not resistant to outliers. Okay? 1 point can greatly, potentially influence everything. Yeah?
Speaking of potential influence, is having diagnostic on your calculator do any harm really on anything else?
I don't think so. I had that question last period. Somebody said, I'm in calculus. Is that going to mess up everything? I don't think so. All right. Now, the reason why... Yeah, what's that?
They have 2 classes?
Yeah, they take them both.
I thought this was our only class.
Yeah, I think they're taking it in the evenings next semester or something. All right, now, why do we need R? Well, you can't trust your eyes. Go to page 141. All right, I got 2 graphs on 141. And if I were asked, which one of those is more linear? Which is going to have a stronger R? I would probably say the bottom one. You guys with me on that? That looks like it's a little more linear. R is a little bit better. It looks like the other one's more, not so linear. They're the same exact graph. They're the same exact graph. They just spread out the X and Y's, right? So your eyeballs, you can't trust them. Right? So that's why we need some sort of mathematical operation to give us a better idea of how strong a line is. Turn to page 145. Now looking at these, they give you kind of the R values for those. Hopefully you could have guessed numbers that were pretty close to that. Take a look at those. think one of the problems you'll do down the road is I'll give you some of these, and I want estimates for R. We kind of agree with those R estimates, okay? Kind of goes in line with this particular. Okay, incredibly important measurement we do in statistics is called the correlation coefficient. In a couple of days, I'm going to explain to you something called the coefficient of determination. You've got to keep the two straight. One is correlation, which means R. The thing we're going to learn later is something else. Okay, so it is important that you learn that vocabulary. All right, this R value tells us the direction and strength of a straight line. Just be careful. Any questions?